Welcome back. Today, we're unlocking one of the absolute core concepts in structural engineering and finite element analysis, the dynamics of beams. I mean, if you've ever looked up at a massive bridge or maybe out the window at an airplane wing and wondered how in the world engineers predict exactly how they're going to bend and react to stress, well, this is exactly how they do it.
So, let's just dive right into the central problem engineers face here. In structural analysis, we can build this massive, highly complex matrix equation that, theoretically, describes the physics of literally any beam. But here's the catch. Because it applies to every single beam out there, it practically applies to absolutely none of them. At least, not until we adapt it. It's just way too generic. So the big question is, how do we take one massive mathematical model and adapt it to fit the specific physical reality of the exact beam we're trying to build?
Well, here is our roadmap for this explainer. We're going to cover Section 1, the finite element model, Section 2, applying boundary conditions, Section 3, Case 1, which is the cantilever beam, Section 4, primary and secondary equations, Section 5, Case 2, the simply supported beam, and finally, Section 6, evaluating support reactions.
Okay, starting off with Section 1, the finite element model. Now, right off the bat, this general model can look like a pretty intimidating wall of matrix math. But let's break it down together. On the left side, we've got our mass term. That's represented by rho AL over 420. Next to that is our stiffness term, EI over L cubed. And then trailing those matrices, you have a whole column of variables, V1, V'1, V2, V'2, all the way down to 3. Basically, those represent displacement, how much the beam moves up or down, and slope, which is how much the beam bends. Right now, in this general starting point, literally everything is an unknown variable. The model accounts for all mass, all stiffness, and all potential movement everywhere. But to actually make it useful for us, we need a filter.
That brings us to Section 2, applying boundary conditions.
This right here is where physical reality steps in to tame the mathematical beast. We do this using an incredibly elegant three-step process to shatter this complex, generic equation into nice, solvable pieces. Step 1, we identify boundary zeros from our physical constraints. Think of physical constraints, like a beam bolted to a solid concrete wall, as our mathematical filters. Step 2, we extract what are called primary equations, and we use those to solve for the displacements we don't know. And step 3, we extract secondary equations to figure out the massive forces happening right at the supports.
Let's look at Section 3, Case 1, the cantilever beam. So, picture a diving board. It's fixed firmly at one end, right? And it's completely free to bounce at the other. Because the left side is bolted solidly into a wall, it physically cannot move up or down, and it physically cannot bend at that exact connection point. We take that physical immobility and translate it directly into mathematical zeros. Displacement at point 1 is 0, so V1 equals 0. The slope at point 1 is 0, meaning V'1 equals 0. And logically, if it literally can't move, it definitely can't accelerate. So our acceleration variables at point 1 are identically 0 too.
Now, by simply plugging in those zeros for V1 and V'1, we brilliantly eliminate whole sections of our matrix. Remember, anything multiplied by 0 just becomes 0. So the first two columns and rows of our generic matrix essentially just vanish from our active problem solving. By just observing the physical limits of the beam, we have cleared out a massive amount of mathematical noise.
Moving on to Section 4, primary and secondary equations.
Because we applied those zeros, our single giant matrix equation naturally splits apart into two distinct, highly useful equations. The first split gives us the primary equations. By definition, these are the equations we extract to solve for the time response of the unknown displacements and slopes, usually using numerical techniques. In plain terms, this is our main tool for calculating exactly how the rest of the beam, the free parts not bolted to the wall, will bounce, move, and bend over time when a force hits it.
Let's look closely at what actually survives our zero filter for the cantilever beam. We are left with displacement 2, slope 2, displacement 3, and slope 3. Basically, these are the free-moving parts of our diving board. These leftover variables represent the specific, unknown physical movements we still need to solve for, and our primary equation is now perfectly sized to do exactly that.
But wait, what about the parts we zeroed out? That data isn't just thrown away. It actually forms our secondary or auxiliary equations. These equations contain the time history of concentrated forces and moments. Basically, once we solve the primary equation and figure out how the beam is bouncing around, we take those solutions and plug them directly back into the secondary equation. Doing this reveals the massive, hidden forces and bending moments happening exactly at the fixed support. It literally tells us how much stress that wall is actually taking.
All right, let's contrast that with Section 5, Case 2, the simply supported beam.
For this one, think of a wooden plank simply resting across two sawhorses. Let's compare the constraints here. Our cantilever restricted both displacement and slope on the left side, right? So V1 and V'1 were 0. But our simply supported beam is just resting on those two sawhorses. The sawhorses stop the beam from falling down, meaning displacement at both ends is 0. That gives us V1 equals 0 and V3 equals 0. But notice this, resting on a sawhorse doesn't stop the beam from bending or pivoting at the ends, so the slope, the V' variables, are absolutely not 0 here.
Because our zeros are now applied to the V1 and V3 components, which represent that restricted vertical movement at both ends, we end up creating a completely different visual puzzle. Our mathematical filter has shattered the generalized equation in a totally new way. The rows and columns that vanish this time are entirely different from the cantilever case.
So, let's look at the resulting primary equation and see what our new reality looks like. Check out our leftover unknown variables now. We have slope 1, displacement 2, slope 2, and slope 3. Because the ends are free to pivot, we now actually have to solve for the bending slope at point 1, which we completely ignored in the cantilever case. I think this proves beautifully how the physical boundary condition dictates exactly what mathematics we are left to solve.
And finally, Section 6, evaluating support reactions.
Just like before, we're going to use our secondary equations, but because our physical supports are now at the two far ends, isolating the secondary equations here allows us to easily calculate the physical forces pushing back at both supports. Specifically, we're looking at the force variables P1 on the left side and P3 on the right side. It tells us with mathematical precision exactly how much weight those two sawhorses are supporting at any given millisecond.
So, the absolutely crucial point here is perfectly summarized by a quote from our source material by Mohammad Tawfik. He states, "Up to this moment, all the procedure may apply to any beam. Differences will appear when different beams are subjected to different boundary conditions." And that really is the core takeaway of this whole explainer. A massive, intimidating matrix is really just abstract math. It's the boundary conditions, the actual physical reality of walls and pins and rollers that act as the magic ingredient turning that theoretical math into real-world structural engineering.
Which leaves us with a pretty fascinating thought to end on today. We've just seen how physical constraints completely rewrite the mathematical matrix, making super complex analysis perfectly solvable. But in the real world, structures break. So I leave you with this. What happens mathematically to these carefully balanced primary and secondary equations when those support reactions, the fixed walls or those resting sawhorses, begin to yield or fail under extreme stress? How in the world does the matrix adapt when the boundary condition itself starts to move? Keep that provocative question in mind as you continue exploring finite element analysis. Thank you so much for diving into this with me today. Keep learning, and I will see you in the next explainer.